kind of vibration is what starts a wave. And the wave is actually the transfer of energy, okay, from one place to another. And there are two different ways that's done, two different kinds of waves. One is called a transverse wave, which is one where if I were to have like a piece of rope, like a clothesline. Do they still have clotheslines? I don't know if they're making them anymore. I'm really dating myself now, because I had clothes on a clothesline. But anyway, the thing is, if I had a rope that went from here and tied on the door, let's say, you guys know this from jump rope, for example, that uses clothesline. Well, anyway, the thing is, you go up and down like this, and you know what's going to happen is you'll have a wave that gets generated, right, and goes along the rope, right, until it hits the door, it reflects back. Now, that's called a transverse wave because if you were to, probably should, maybe we'll try this in the lab when we get there, if we have a piece of rope. If you take that piece of rope and tie like something brightly colored, something small on the rope tightly, you guys would see that while you're doing this and the wave energy is going in that direction, that little bit of rope is only going up and down. It's not moving in back and forth at all. It's only going up and down. Transverse is another way of saying perpendicular to. And that's what that means. It's the motion of the wave is the wave energy is perpendicular to the actual direction that the wave is going. Okay, so that's what that's called a transverse wave. All light, for example, is made up of these transverse waves, you know, for example. The other kind of a wave is one like this, where you need to have some kind of a medium. And this is a sound wave, for example. And what you do, like when I'm speaking or you're speaking, what's happening is our vocal cords are compressing the air in one direction, first of all, and then they're pulling back and rarefying it, or making it less dense. And then they get dense again and less dense, and dense and less dense. And that's what causes the vibration that's in the air would look like this. So in this case, you can see that the wave, if the sound wave is going that way, so are the molecules. They're not actually moving that way, but they're going back and forth, but in the same plane, right, as the wave energy. So that's the other kind. There's only two kinds of waves, those two. All right. So, but that's you know, as I say, this one is primarily a sound wave. This one is primarily electromagnetic wave of one kind or another. But they are the two kinds of waves. Out in the Gulf, when you're out in water, the water is actually a combination of these two. If you were to follow a water molecule as a wave went by, the water molecule would go up and down, but it would make like a circle, but it would go back to where it started from, always. Okay, so it's a combination of those two. But if that were true, how come if you throw something overboard in a boat, why doesn't it stay right where it is? What do you think? If that's true, right, it should stay right there, right? As the waves go by, it should just stay there. Why doesn't it? What do you think? This is a common sense question. It's not. Sorry?
What was the question? What was the question? Why
does it move? So in other words, I finish this ball and I'm a bad person. I throw it overboard, right? Why does it move? What do you think?
Does it like generate its own wave?
No.
Can't solve it.
No. What do you think?
Gravity.
No.
The water.
Imagine your boat. If you had a boat out there and you didn't anchor, why did the boat stay there? What moves the boat?
Energy of the waves.
No, the wave energy is going to just keep the boat right where it is. This is such a simple thing you're going to say.
The wind.
The what? The wind is one thing. That's right. Blowing on it, right? The wind can blow it. And what else can move it like that?
Currents.
Currents, right, exactly. But I just wanted you to, I told you it was very simple, the two things. But the point is that without those, it will just sit there in one place. I just want you to realize, even as the wave is going by, it's just going like up and down, staying here. But then with currents, it will move, or if wind blows on it, it'll move, of course. Okay, but I don't want to go too long with this. Now, pendulum, we're going to do a pendulum lab this week. I have to remember to bring in extra string to make sure we have it in that crazy lab that we've got where nobody seems to be cleaning it up. But in any case, with this, one of the things about a pendulum is, and you guys will see this when we do our lab also, is that the period of the pendulum, the period is the time it takes from wherever you start till it gets back to where it started, all right? The time it took to go out and back again. That's called the period, all right, of the motion, of the vibration, or the period of the wave is going to be that way when you get back to your starting point. But if we just look at a pendulum, it turns out that, and Galileo observed this, he was, when he was a student in college in Pisa, Italy, they used to have they still have this big chandelier there. I have a picture of it. I gotta find that, well, I guess I still can show you guys. I have to get it on my flash drive because we don't have I don't know if we have a DVD player. We do have one, it should be able to play it, that CD. Anyhow, what Galileo noticed was, like when I saw it a few years ago, I was over there and I saw it, it's with lights, okay? A big chandelier in the middle of the cathedral, okay, the big thing. But in his day, that same chandelier was filled with candles. They didn't have electric lights then. It was just candles. So once every, however often they had to change the candles, they would go up to the next level in the cathedral. There was like a walkway all around the inside of the cathedral, and somebody with a rope would then pull the chandelier over, all right, tie it up, right, right there, and then change all of the candles, right, relight the candles, and then let the chandelier go back to the center again, right? Make sense? What Galileo noticed as a young man, and remember, Galileo, the main thing he did was observe. He was a really observant guy. This is the kind of thing I would never have thought to look at. But what Galileo figured out was, when they let that chandelier go, it didn't matter if they let it go, say, a foot or two from where the equilibrium point was and has to swing back and forth until it comes to rest, or if they let it go where it's really close to its equilibrium position. He found out that the period, the time it took for that great big chandelier to move from one place back to where it started was the same. So in other words, if you had it further out, it would just move faster, but it would take, let's say it was 1 second, and then you had it closer, it would still take that 1 second to go back and forth. Now, of course, he didn't know what to do with that. After he died, Isaac Newton came along, and he figured the math part of all that out. But I just want you to see here, the length of that pendulum is what makes is what controls the time of that period, back and forth. The shorter the pendulum, the faster it moves, and the quicker the period. And some of you may have a pendulum clock at home, and if you do, I think you'll know from adjusting it, you'll know that if it's going too fast, what you would do is you would adjust the pendulum so the weight would go down a little more. You'd make it a little longer, all right? And so you can then slow down the motion, or if it's too slow, you would raise up the weight. Those of you that have a pendulum clock would know that. I happen to have one. It's not even mine, it's my wife's. It's our second marriage, so she brought a lot of stuff. So anyhow, that's one of the things she brought was that very nice clock. So she told me something else too, a trick with that clock. Was it chimes? She sets it for 5 minutes ahead. So like, if you wanted to say, leave the house at 6 o'clock and you're getting ready to go somewhere, right? Then it would chime at 5 minutes to 6. You say, oh, I got 5, I got to get going here. She told me to use that as a trick to keep yourself on time, just to have it run a little fast, have it run 5 minutes fast. But anyhow, this is the important thing, is that the length is important and gravity is important. If gravity changes, then the swing will be different. This motion is called simple harmonic motion, is what it's called in science. Okay, here's the wave again. This is a transverse wave. I just want to show you the definitions of these things. You guys seen this before? Probably in another course somewhere? No? Yes? Okay, well, all right, the wave looks like this. Now you can see this is a repeat unit. I can take this and move it over here, and you can see it's going to do the same thing again. So this distance here is going to be, if it's time, if this axis is time, this would be the period. If it's distance, then this is what's called the wavelength, because that's the repeat unit, is the wavelength. Okay? So, the time for one wavelength to pass is also called a period. I just wanted to point that out to you. So, but you guys see the difference between the crest, the trough, the amplitude, right? The amplitude isn't from the bottom to the top. is from the midline, either to the bottom or the top, either one. They're going to be the same. My drawing is not so good, but they would be the same. And the distance of that repeat unit is going to be, is called the wavelength. Okay? So far? Okay. Then, the number of vibrations, the number of periods that you have in 1 second is called the frequency. So, don't worry, there's a nice easy relationship between the frequency and the period. One is the inverse of the other. In other words, if you have a period on that pendulum of, say, 2 seconds, what's the frequency? Well, if the period is 2 seconds, 1/2 is a half. That's what the frequency is. A half. In other words, every second you're going through half the motion. So that's what I was trying to show you here. 1 vibration a second gives you a frequency of 1, but if you have 5 vibrations in a second, then that's a frequency of 5. So you'll have 5 vibrations, there'll be 5 cycles per second, but then the period will only be 1/5 of that. And you see, we used to, when I was in school, we used to call the unit for frequency cycles per second, or CPS. You'll still see that used today in some